No-till agriculture became powerful not because it was universally superior, but because it offered a narrative that felt morally correct, operationally simple, and emotionally satisfying. It promised a system where restraint replaced intervention, where nature compensated for human withdrawal, and where complexity dissolved into patience. The appeal was immediate: stop disturbing the soil, keep residue on the surface, let biology rebuild structure, and productivity will stabilize naturally. For a long time, this promise appeared to work. In low-pressure systems, under moderate yield expectations, and within forgiving climatic zones, no-till delivered measurable improvements. Surface erosion decreased, organic matter increased in the upper profile, fuel costs dropped, labor efficiency improved. These gains were real, and they deserved recognition. The problem began when success turned into certainty. As no-till spread, it stopped being treated as a conditional management choice and started being presented as a universal solution. The method was no longer evaluated by context, but defended by principle. Any failure was attributed not to the system itself, but to insufficient time, incomplete adoption, or external stressors. The method became insulated from critique. High-yield agriculture does not tolerate insulation. When production systems push toward biological and physical limits, every assumption is tested. Nutrient demand intensifies. Root exploration becomes non-negotiable. Water dynamics shift from convenience to constraint. Machinery traffic increases. Timelines compress. Margins tighten. In this environment, systems are not judged by intention, but by performance under pressure. This is where no-till begins to fracture. The central lie is not that no-till works. The lie is that it works everywhere, indefinitely, and without structural consequences. High-yield systems expose this lie because they remove the buffer that allows inefficiencies to hide. They operate at extraction rates that exceed the natural recovery speed of many soils. They demand synchronization between chemical availability, physical structure, biological activity, and climatic timing. Any lag in this chain creates loss, and loss compounds rapidly at scale. No-till, by design, prioritizes biological recovery over mechanical correction. This trade-off is not inherently wrong. It becomes problematic when biological processes are expected to compensate for physical constraints faster than they realistically can. Soil does not fail loudly. It fails quietly, layer by layer. Surface indicators often remain positive. Residue cover looks ideal. Organic carbon measurements near the top improve. Aggregate stability tests show progress. These metrics reinforce confidence and delay scrutiny. Meanwhile, subsurface conditions evolve independently, governed by traffic load, moisture cycles, and particle rearrangement that biology alone cannot fully reverse in compressed timeframes. Roots are the first to notice. Yield is the last. High-yield crops require depth. Not symbolic depth, but functional depth. Roots must penetrate, branch, respire, and exchange across the full profile. Water must infiltrate beyond the surface. Nutrients must be accessible where roots actively uptake, not merely where residues decompose. When no-till systems are pushed beyond their adaptive range, this depth becomes compromised. Dense layers form, pore continuity degrades, oxygen diffusion slows, nutrient stratification intensifies. These processes do not announce themselves with catastrophic failure. They express as yield plateaus, inconsistent performance, and rising input dependency. Because these outcomes are gradual, they are often misdiagnosed. Yield stagnation is blamed on genetics. Disease pressure is blamed on climate. Input inefficiency is blamed on markets. The system itself remains protected by ideology. This protection is reinforced socially. No-till has become more than a practice. It has become an identity. Questioning it is interpreted as regression rather than analysis. This cultural shield delays corrective action and amplifies losses when correction finally becomes unavoidable. High-yield agriculture cannot afford identity-based management. Every system is a compromise between speed, stability, and control. No-till sacrifices speed of correction for long-term stability. That trade-off works when extraction pressure is low and timelines are flexible. It fails when yield expectations demand immediate responsiveness. The assumption that soil biology will always self-correct physical limitations ignores scale. Biological aggregation operates on seasonal and multi-year cycles. Compaction from modern equipment can occur in a single pass. Traffic-induced density is not distributed evenly. It concentrates at specific depths and zones, creating layered resistance that roots and water must navigate. Without mechanical intervention, these layers persist. In moderate systems, persistence may be tolerable. In high-yield systems, it becomes a ceiling. This ceiling is not visible in early adoption stages. In fact, no-till often produces short-term gains that mask long-term constraints. Reduced erosion improves nutrient retention. Surface moisture conservation enhances early growth. Weed dynamics shift favorably for a time. These benefits reinforce commitment precisely when scrutiny should increase. The system appears to be working, so it is pushed harder. More yield, more traffic, more extraction. Eventually, the balance tips. What follows is not collapse, but inefficiency. Inputs increase to maintain output. Variability widens between fields and seasons. Predictability declines. Management becomes reactive instead of strategic. At this stage, no-till defenders often respond with escalation rather than evaluation. More cover crops, more biological amendments, more surface-focused interventions, each adds complexity, cost, and management load, while the underlying physical constraints remain largely untouched. This is not sustainability, it is avoidance. The purpose of agriculture is not to preserve systems. It is to produce outcomes. Systems are tools, not doctrines. Any method that cannot be adjusted under pressure becomes a liability, regardless of how well it performs under ideal conditions. High-yield farms expose this reality because they operate without margin for sentimentality. They demand functional depth, synchronized nutrient delivery, and structural resilience. When a system fails to deliver these consistently, it must be modified or replaced. No-till resists modification by design. That resistance is the root of its failure at scale. This analysis does not argue for indiscriminate tillage. It does not dismiss conservation goals. It does not deny the environmental benefits no-till can provide under appropriate conditions. It simply rejects the assumption that one method can satisfy all production goals across all environments indefinitely. High-yield agriculture is an engineering problem constrained by biology. Engineering without adjustment fails. Biology without structure drifts. The comfortable lie is believing that restraint alone is management. In the sections that follow, the failure mechanisms will be examined in detail. Soil physics, nutrient stratification, root architecture, climate volatility, economic feedback loops, each contributes to the same conclusion. No-till is not broken, but it is limited, and those limits become unavoidable when yield matters most. This is where ideology ends, and system design begins. To understand why no-till fails in high-yield systems, it is necessary to first acknowledge where it succeeds. Ignoring its strengths weakens the critique and turns analysis into ideology, which is precisely the mistake that no-till absolutism makes in reverse. No-till performs exceptionally well in environments where biological recovery can keep pace with physical and chemical demand. These environments share common characteristics: moderate yield targets, stable or predictable rainfall patterns, soils with inherent structural resilience, and operational systems that limit traffic intensity and timing errors. In these contexts, no-till is not just viable, it is efficient. Surface residue moderates temperature fluctuations. Moisture loss through evaporation is reduced. Microbial communities benefit from consistent carbon inputs. Fungal networks develop with minimal disruption. Aggregate stability in the upper soil layers improves, often significantly. Over time, erosion is reduced to near zero, which alone can justify adoption in vulnerable landscapes. These outcomes are measurable and repeatable. The key factor is that the system is not under constant structural stress. Yield expectations remain within the adaptive capacity of the soil. Root systems do not need to aggressively penetrate compacted zones to meet water demand. Nutrient uptake occurs largely within the biologically active layers. Machinery traffic, while present, does not accumulate density faster than biological processes can reorganize pore space. In other words, no-till works when the soil has time. Time is the variable that high-yield systems remove. As yield targets increase, extraction accelerates. More biomass is removed, more nutrients are exported, root systems are forced to explore deeper and faster. Water demand becomes less forgiving of shallow or discontinuous pore networks. At the same time, modern equipment becomes heavier, wider, and less flexible in timing. Traffic intensity increases, not necessarily because of poor management, but because scale demands it. The balance shifts. In these conditions, no-till transitions from a system of regeneration to a system of accumulation. Residue accumulates faster than it decomposes. Nutrients concentrate where residues break down. Density accumulates where traffic repeats. Biology responds, but not uniformly and not fast enough to prevent stratification. This is where misunderstanding begins. Many failures attributed to poor no-till execution are actually failures of scale mismatch. The system is asked to deliver performance beyond its design parameters. When it cannot, the response is often to intensify the same mechanisms that are already lagging behind. More residue, more covers, more surface biology. These interventions may improve certain indicators, but they do not address the core limitation: physical constraint at depth. High-yield systems expose this constraint because they do not tolerate inefficiency. A minor reduction in root depth may be irrelevant at moderate yield levels. At high yield, it becomes decisive. A slight delay in infiltration may be absorbed in forgiving climates. In volatile ones, it creates crop failure. The distinction is not philosophical. It is operational. No-till is optimized for stability, not responsiveness. High-yield agriculture demands responsiveness above all else. It requires the ability to reset soil conditions when structure degrades faster than biology can repair it. No-till resists this reset, both mechanically and culturally. This resistance is often justified by long-term thinking. The argument suggests that any short-term gain from mechanical intervention compromises long-term soil health. The flaw in this reasoning is the assumption that long-term health is preserved by inaction. In reality, unmanaged stress accumulates. Biological systems are adaptive, but they are not omnipotent. They operate within physical boundaries. When those boundaries are exceeded, biology adapts around constraints rather than eliminating them. Roots flatten. Microbes shift niches. Water pathways reroute laterally instead of vertically. The system stabilizes, but at a lower functional level. From the surface, it still looks healthy. This illusion is strongest in fields with good residue cover and visible biological activity. Soil pits often reinforce it. The top layer appears dark, aggregated, and alive. But depth tells a different story. Below the biologically active zone, resistance increases sharply. Roots thin. Pores collapse. Chemical gradients steepen. High-yield crops cannot negotiate with this profile. They require continuity. Roots must move seamlessly from surface to depth. Water must infiltrate and drain without interruption. Nutrients must be accessible where roots are most active, not where residue happens to decompose. No-till systems often fail to provide this continuity at scale. This does not mean that tillage is inherently superior. It means that mechanical intervention remains the fastest method to correct physical constraints when they exceed biological repair rates. Ignoring this fact does not make it disappear. It only delays correction until losses accumulate. The farms where no-till works best tend to share another characteristic: they operate with flexibility. Yield expectations are adjusted based on conditions. Inputs are moderated. Profitability is measured across stability rather than maximization. These systems prioritize risk reduction over peak performance. High-yield farms operate differently. They pursue optimization. They invest heavily in genetics, nutrition, protection, and technology. They rely on precision, not tolerance. Variability is the enemy. Predictability is the goal. When no-till introduces variability through uneven rooting, inconsistent infiltration, or stratified nutrient availability, it undermines the very foundation of high-yield management. This is why no-till failures are often first detected in data, not in appearance. Yield maps show patterns. Variable rate prescriptions become less effective. Response curves flatten. These signals are frequently dismissed or misinterpreted because they conflict with the visible narrative of soil health. Data does not lie, it waits. Eventually, the system reaches a point where compensation becomes too expensive. Inputs rise faster than returns. Yield gains require disproportionate investment. At this stage, the farm is no longer managing soil. It is managing symptoms. This is not a failure of discipline. It is a failure of alignment. No-till is aligned with conservation under moderate pressure. High-yield agriculture applies extreme pressure by definition. Expecting the same system to thrive under both is not optimism. It is denial. Recognizing where no-till works is essential, because it defines its boundaries. Systems fail not because they are wrong, but because they are misapplied. The danger lies in refusing to define limits. High-yield farms do not need belief systems. They need tools that respond to reality. In the next section, the analysis moves below the surface. The focus shifts from philosophy to physics. Because regardless of method, soil obeys mechanical laws, and those laws are the first to be violated when scale increases. Every agricultural system, regardless of philosophy, is ultimately governed by physics. Biology operates within physical space. Chemistry reacts within physical constraints. When physical structure degrades, neither biological activity nor chemical correction can fully compensate for long. This is where no-till begins to encounter limits that cannot be negotiated away. Soil is a load-bearing medium. It supports machinery, stores water, transmits gases, and allows root penetration. These functions depend on pore architecture, not on ideology. Pores must be connected, stable, and appropriately distributed across the soil profile. When that architecture is altered unfavorably, function declines regardless of surface appearance. High-yield systems alter this architecture aggressively. Modern agricultural machinery applies enormous point loads to the soil, especially under less than ideal moisture conditions. Even with controlled traffic and wide tires, stress is transmitted downward. The deeper the stress travels, the harder it becomes for biological processes to reverse it. In conventional systems, periodic tillage disrupts these compacted zones mechanically. In no-till systems, this disruption is intentionally avoided. The assumption is that roots, microorganisms, freeze-thaw cycles, and wet-dry dynamics will gradually restore structure. This assumption holds only when stress accumulation is slower than biological repair. High-yield systems reverse that relationship. Traffic occurs repeatedly in the same zones. Harvest timing is dictated by crop maturity and weather windows, not by ideal soil conditions. Loads are heavier due to yield itself. Each pass contributes incrementally to subsoil densification. Over time, discrete compacted layers form at predictable depths. These layers are not catastrophic barriers. They are resistive interfaces. Roots respond to resistance by altering growth patterns. Instead of penetrating vertically, they proliferate laterally. Root diameter decreases. Branching increases near the resistance zone. This adaptation allows survival, but it reduces effective rooting depth and limits access to deep water reserves. Water responds similarly. Infiltration slows at the compacted layer. Above it, water accumulates. Below it, soil remains dry longer. This creates alternating zones of saturation and drought stress within the same profile. No-till systems often mask this behavior because surface residue reduces evaporation and smooths moisture fluctuations. The surface stays moist, reinforcing the perception of improved water management. Meanwhile, deeper layers experience increasing hydraulic discontinuity. High-yield crops cannot tolerate this inconsistency. During early growth, shallow moisture may be sufficient. As biomass increases, transpiration demand rises exponentially. At this stage, shallow rooting becomes a liability. Crops become highly sensitive to short dry periods. Stress appears abruptly, even when total soil moisture remains adequate at depth. This is not a rainfall problem. It is an access problem. No-till advocates often point to increased earthworm activity as evidence of deep structure repair. While biopores do contribute to vertical connectivity, their distribution is uneven and their capacity limited. They do not create the uniform, load-bearing pore network required to support dense, high-demand root systems across entire fields. Biological repair is selective, mechanical stress is not. Another physical constraint emerges from the accumulation of residue and the absence of mixing. Surface layers become increasingly organic and porous, while underlying layers remain mineral-dense and resistant. The contrast between these zones increases over time, creating sharp gradients in bulk density and hydraulic conductivity. Gradients are weak points. Roots crossing sharp density gradients experience mechanical impedance and physiological stress. Nutrient uptake efficiency declines. Hormonal signaling changes. Plants allocate more energy to root exploration and less to reproductive development. Yield potential erodes quietly. Because these effects are distributed spatially, they manifest as variability rather than uniform failure. Some zones perform well, others lag. Management becomes more complex. Variable rate strategies attempt to compensate, but they address symptoms rather than structure. At high yield levels, variability itself becomes a cost. Physical limits also interact with temperature. Residue-covered surfaces warm more slowly in spring. While this can be beneficial in hot climates, it delays early root development in cooler regions. When combined with subsoil resistance, early season growth becomes constrained both thermally and mechanically. Delayed early growth compresses the crop's effective growing window. To compensate, plants must grow faster later. This increases peak demand for water and nutrients, further stressing a system already limited by depth. Again, the issue is not no-till in isolation. It is no-till under compounded pressure. Physics imposes nonlinear penalties. Small increases in resistance can produce disproportionate reductions in flow, whether of roots, water, or gases. Once these thresholds are crossed, system performance drops rapidly. Biology cannot override this. It can only adapt around it. Adaptation around constraints leads to stability at lower performance levels. The system finds a new equilibrium, but that equilibrium often lies below the yield targets that justified the investment in the first place. This is where no-till fails silently. The surface remains visually convincing. Organic matter tests near the top improve. Biological activity measurements remain high. These indicators suggest success, even as physical functionality declines below. High-yield agriculture does not reward appearances. It rewards consistency under stress. When physical limits constrain root access, every other input becomes less efficient. Nutrients cannot be fully utilized. Water cannot be reliably accessed. Protection products face greater pressure because stressed plants are more vulnerable. Input efficiency drops. Costs rise. Returns flatten. At this point, the system is often defended more aggressively rather than adjusted. Mechanical intervention is delayed because it conflicts with identity and long-term narratives. Meanwhile, losses accumulate year after year. Eventually, correction becomes unavoidable. But by then, it is more disruptive and more expensive than it would have been earlier. Understanding the physical limits of no-till is not an argument for abandonment. It is an argument for realism. Systems must be evaluated based on their ability to absorb stress at scale, not on their theoretical elegance. High-yield systems magnify physical weaknesses. They do not create them. In the next section, the focus shifts from structure to chemistry. Because even when roots manage to penetrate, nutrient dynamics under no-till introduce another layer of limitation that becomes increasingly visible as yield expectations rise. Chemical fertility under no-till systems is often discussed in terms of abundance rather than accessibility. This distinction is harmless at low yield levels. At high yield, it becomes critical. Nutrients do not generate productivity by existing in the soil. They generate productivity by intersecting active roots at the right time, in the right form, and at the right depth. No-till disrupts this intersection. By eliminating soil mixing, no-till concentrates nutrient cycling near the surface. Crop residues decompose where they fall. Organic acids, microbial activity, and nutrient release are therefore vertically compressed. Phosphorus, potassium, calcium, magnesium, and many micronutrients accumulate disproportionately in the upper layers of the soil profile. From a soil test perspective, this often looks positive. Surface samples show improving fertility. Organic matter rises. Cation exchange capacity increases. These results reinforce confidence in the system and justify continued adherence. But high-yield crops do not operate on surface averages. They operate on root-scale realities. Roots respond to moisture gradients first. In dry periods, they move downward. In wet periods, they avoid anaerobic zones. Their spatial distribution shifts dynamically throughout the season. When nutrients are concentrated near the surface while roots are forced deeper for water, uptake efficiency collapses. This creates a paradoxical condition. Soils test rich, crops behave deficient. The response is usually corrective rather than structural. More fertilizer is applied. Placement strategies become increasingly complex. Foliar feeding is layered on top. Biological solubilizers are introduced. Each intervention adds cost and management complexity while masking the underlying misalignment between nutrient location and root activity. Stratification also alters chemical interactions within the soil. High concentrations of phosphorus near the surface can reduce zinc and copper availability. Potassium accumulation can interfere with magnesium and calcium uptake. pH gradients intensify, creating chemically distinct zones that roots must traverse. In high-yield systems, roots do not have the luxury of avoidance. They must function across the entire profile. Chemical discontinuities introduce physiological stress that does not always present as classic deficiency symptoms but still reduces efficiency. Another critical factor is nitrogen dynamics. No-till systems tend to retain nitrogen near the surface, particularly in residue-rich environments. While this can reduce leaching in some contexts, it also increases vulnerability to volatilization and denitrification during wet periods. When surface layers remain moist and oxygen diffusion is limited, nitrogen losses accelerate. At the same time, deeper soil layers may remain nitrogen poor. Roots encountering compacted zones often slow or stop, further limiting access to deeper nutrient pools. The result is a system where nitrogen availability fluctuates sharply over time and space. High-yield crops require stability. Nitrogen instability translates directly into yield variability. Attempts to stabilize nitrogen supply through split applications, inhibitors, and precision timing help, but they do not eliminate the structural issue. The system remains dependent on constant correction rather than inherent alignment. Potassium presents a similar challenge. As a relatively immobile nutrient, potassium accumulates where it is placed and released. Under no-till, this is predominantly near the surface. In dry conditions, surface potassium becomes functionally inaccessible just as plant demand peaks. Deeper reserves, if present, remain underutilized due to restricted root access. The result is water stress compounded by nutrient stress, even when total soil reserves are adequate. This is why high-yield no-till systems often show diminishing returns to fertilization. Inputs increase, but response curves flatten. The problem is not insufficient supply. It is inefficient delivery. Chemical stratification also interacts with biology in nonlinear ways. Microbial populations adapt to nutrient-rich surface zones. Activity intensifies there while deeper layers remain comparatively inert. This reinforces vertical separation rather than integration. Biology follows resources. Roots follow water. Yield follows alignment. No-till frequently disrupts this alignment. In moderate systems, the consequences are subtle. Yield may plateau slightly. Variability may increase marginally. These effects are tolerable. In high-yield systems, they are amplified. Small inefficiencies translate into significant losses when multiplied across hectares and seasons. Because stratification develops gradually, it often escapes attention until it becomes severe. Early soil tests look encouraging. Only later do corrective recommendations escalate sharply. At that point, restoring balance without physical mixing becomes increasingly difficult. Deep banding is sometimes proposed as a solution. While effective in certain contexts, it introduces new complexity and cost. Equipment investment rises, operational flexibility decreases, placement accuracy becomes critical, errors carry higher penalties. Again, the system compensates rather than corrects. High-yield farms value simplicity not as ideology, but as risk management. Systems that require constant fine-tuning to maintain baseline performance are fragile under real-world conditions. Chemical fertility under no-till tends toward fragility as yield pressure increases. This does not mean that tillage guarantees better nutrient management. Poorly managed tillage can create its own inefficiencies. The distinction lies in optionality. Tillage provides the ability to reset nutrient distribution when stratification becomes limiting. No-till removes that option by default. When reset is impossible, systems rely on escalation. More inputs, more precision, more intervention layered on intervention. Eventually, the marginal cost of correction exceeds the marginal gain in yield. At that point, the system has failed economically even if it survives agronomically. High-yield agriculture cannot afford systems that require perpetual compensation. It requires systems that maintain alignment under pressure. Nutrient stratification under no-till is not immediately catastrophic. That is precisely why it is dangerous. It degrades efficiency slowly, quietly, and convincingly. In the next section, the analysis moves from nutrients to roots themselves. Because roots are the interface where physics and chemistry become biology, and their behavior under no-till reveals the cumulative impact of all previous constraints. Roots are the most honest diagnostic tool in agriculture. They do not care about narratives, certifications, or intentions. They respond only to resistance, oxygen, water, and chemical signals. When a system works, roots tell the story clearly. When it does not, they reveal the failure long before yield monitors do. In high-yield no-till systems, roots are forced to negotiate an increasingly contradictory environment. The surface layer is often loose, biologically active, and nutrient-rich. Below it, resistance increases sharply. Oxygen availability fluctuates. Chemical gradients intensify. The root system must constantly adapt its architecture to survive, even before it can focus on supporting yield. This adaptation comes at a cost. Instead of prioritizing vertical penetration, roots allocate energy to lateral expansion near resistance zones. Fine root density increases where pores allow it. Root hairs proliferate in nutrient-rich but shallow layers. These changes help maintain uptake in the short term, but they fundamentally limit the plant's ability to buffer stress. High-yield crops are not built for compromise. They are built for access. Deep, continuous rooting provides redundancy. It allows plants to access water during dry periods, oxygen during wet periods, and nutrients across variable chemical zones. When rooting depth is restricted or inconsistent, redundancy disappears. Stress becomes binary. Either conditions are perfect or performance drops sharply. No-till systems under high pressure often produce root systems that look busy but are inefficient. There is mass, but not reach. Density, but not depth. From a visual standpoint, this can be misleading. A dense root mat near the surface can appear healthy, even as the plant remains vulnerable to transient stress. This vulnerability expresses itself during critical growth stages. During rapid vegetative growth, shallow systems may suffice. During reproductive stages, demand peaks. Water uptake must increase dramatically. Nutrient flow must remain uninterrupted. Any limitation at this stage translates directly into yield loss. Roots that fail to access deep moisture during brief dry spells cannot recover fully, even if rain returns later. Stress during flowering, grain fill, or pod set leaves permanent marks. In high-yield no-till fields, these losses often appear patchy. Zones with slightly better structure perform well. Zones with marginal resistance underperform. Variability increases, complicating management and reducing predictability. Root health is also tightly linked to disease dynamics. Poorly aerated zones favor pathogenic organisms. Roots stressed by mechanical resistance and oxygen limitation are less capable of defending themselves. In no-till systems, residue retention can increase inoculum pressure at the surface while subsurface stress weakens root defenses. The result is a system where disease pressure is both elevated and harder to manage. Chemical protection becomes more frequent. Biological control becomes less reliable. The crop enters a defensive posture that diverts resources away from yield formation. Again, the issue is cumulative. No single factor causes failure. Root stress accumulates quietly until resilience collapses. Another overlooked aspect is root turnover. In healthy, deep systems, roots are continuously replaced across the profile. Old roots decay, creating channels that new roots exploit. This process builds long-term structure and resilience. In restricted systems, turnover becomes concentrated near the surface. Deep channels are scarce. Biological repair is localized. The subsoil remains largely disconnected from the regenerative cycle. This creates a feedback loop. Restricted roots limit biological activity at depth. Limited biology slows structural repair. Slow repair further restricts roots. High-yield systems accelerate this loop because extraction rates are high and recovery windows are short. Attempts to stimulate deeper rooting through genetics or biological additives have limited impact when physical resistance dominates. Roots cannot express genetic potential in an environment that constrains movement. Biology cannot create pore space where mechanical stress persists. At this point, the system relies increasingly on favorable weather to compensate. When weather cooperates, yields remain acceptable. When it does not, losses are severe. Dependence on weather is not resilience. It is exposure. High-yield agriculture seeks to minimize exposure. It invests in irrigation, drainage, fertility, and protection precisely to reduce dependence on uncontrollable variables. A soil system that amplifies weather sensitivity undermines that objective. Root architecture under no-till is not inherently flawed. In balanced systems, it can be remarkably efficient. The failure occurs when root demands exceed the system's capacity to provide continuous access. This mismatch is subtle. It does not announce itself as root death or crop failure. It presents as marginal inefficiency that compounds over time. Yield ceilings emerge not because plants cannot grow, but because they cannot grow optimally when it matters most. The tragedy is that by the time root limitations become obvious, they are difficult to reverse without significant intervention. Years of accumulated resistance and stratification cannot be undone quickly or cheaply. Early correction is far less disruptive. Delayed correction is far more costly. This is why high-performance farms monitor roots aggressively. They dig, they measure, they compare across systems and seasons. They treat root behavior as a leading indicator, not a postmortem. No-till systems that ignore root signals do so at their own risk. In the next section, the analysis expands beyond the soil profile and into climate interaction. Because even well-managed systems are ultimately tested by variability, and no-till responds to climate stress in ways that become increasingly problematic as yield expectations rise. No-till systems are built on the assumption of relative stability. Stable moisture patterns, predictable seasons, gradual change. That assumption is becoming increasingly detached from reality. Climate volatility is no longer an exception. It is the baseline. High-yield agriculture magnifies the impact of this volatility because it operates close to physiological limits. Crops are pushed harder, cycles are tighter, and tolerance for disruption is minimal. In this context, soil systems must absorb shocks, not amplify them. No-till often amplifies them. In wet years, residue retention slows soil warming and increases surface humidity. While this can reduce evaporation, it also prolongs saturation, limits oxygen diffusion, and increases disease pressure. Root growth slows precisely when early vigor is critical. Delayed establishment compresses the effective growing season and increases later demand peaks. In dry years, the opposite problem emerges. Shallow rooting, caused by physical resistance and stratification, limits access to deep moisture. Surface protection delays stress initially, but once surface moisture is depleted, crops decline rapidly. Stress appears suddenly and recovery is incomplete. The system performs well until it does not. This binary response is dangerous in high-yield systems. Resilient systems degrade gradually under stress. Fragile systems fail abruptly. No-till, under high pressure, tends toward fragility. Another issue is timing. Climate volatility narrows operational windows. Planting, spraying, and harvesting must occur when conditions allow, not when soils are ideal. Traffic under marginal moisture conditions becomes unavoidable. Each compromised pass contributes to subsurface damage that no-till cannot easily correct. The result is a ratchet effect. Damage accumulates, recovery lags. Attempts to buffer climate stress through biological intensification help at the margins but do not change the structural reality. Biology adapts slowly. Climate shocks occur quickly. When these timelines diverge, systems lose coherence. High-yield farms need optionality. They need the ability to intervene when conditions shift. No-till limits that ability by design. What begins as conservation becomes constraint. Climate volatility does not punish systems evenly. It punishes rigidity. The systems that survive are not those with the strongest ideology, but those with the greatest capacity to adjust. In high-yield agriculture, adjustment speed matters as much as long-term vision. No-till struggles when speed becomes critical. In the next section, the focus shifts from agronomy to economics. Because when systems fail, they do not fail first in yield. They fail first in margins. High-yield systems rarely collapse dramatically. They erode. Margins thin first. Efficiency declines quietly. The operation keeps running, but it requires more correction, more inputs, and more attention just to maintain the same output. This is where no-till begins to fail economically before it fails agronomically. Yield stagnation under no-till is often subtle. Fields do not crash. They plateau. Response to fertilizer flattens. Variability increases. Management becomes reactive. These signals are easy to rationalize individually. Together, they indicate systemic inefficiency. Input costs rise in predictable ways. More fungicides to manage residue-driven disease pressure. More micronutrients to correct stratification effects. More nitrogen strategies to stabilize availability. Each addition feels justified. None addresses the structural cause. The cost structure becomes heavier and more complex. High-yield farms depend on predictability. Planning input investment requires confidence in response. When soil function becomes inconsistent, that confidence disappears. Risk increases. Margins compress. Another hidden cost is operational inflexibility. No-till systems often require tighter timing and more precise execution to avoid compounding problems. Delays or errors carry higher penalties. This reduces the farm's ability to adapt under real-world constraints. Labor stress increases. Decision fatigue increases. Management bandwidth narrows. These costs do not appear on balance sheets directly, but they affect performance. High-performing operations understand that complexity itself is an expense. Eventually, correction becomes unavoidable. Compaction must be addressed. Nutrient profiles must be reset. These interventions are more disruptive and costly after years of delay. Yield losses during transition further erode profitability. At that point, no-till has not preserved capital. It has deferred costs with interest. This is not an argument against conservation. It is an argument against ignoring economic feedback. Systems that require constant compensation to maintain baseline performance are not efficient. They are fragile. High-yield agriculture does not reward fragility. In the next section, the focus shifts to what actually works. Not ideology, but practice. Not absolutes, but strategies that high-performance farms use to stay productive under pressure. High-performance farms do not argue about systems. They design them. The distinction is subtle but decisive. Instead of committing to a single method, they build management frameworks that can adapt as conditions change. The common pattern is not abandonment of no-till, but its limitation. Strategic tillage is used as a corrective tool, not as a routine practice. Compacted layers are mechanically addressed when biological repair falls behind. Nutrient profiles are rebalanced when stratification becomes limiting. The objective is not disturbance, but restoration of function. These interventions are targeted. Depth, timing, and intensity are chosen based on data, not habit. Yield maps, soil resistance measurements, root observations, and moisture dynamics guide decisions. The system remains mostly undisturbed, but not untouchable. Residue is managed, not accumulated blindly. Surface cover is adjusted to climate, crop, and soil type. Excess residue is reduced when it creates thermal, disease, or operational constraints. Conservation remains a goal, but it does not override performance. Biology is supported where it works. Carbon inputs are maintained. Cover crops are selected for function, not symbolism. Root depth, not just biomass, is prioritized. Biological products are used to enhance efficiency, not to compensate for structural failure. Rotation is treated as a structural tool. Different root architectures are leveraged to explore soil volume, redistribute nutrients, and disrupt compaction patterns. Diversity is applied with intent. Most importantly, these farms retain optionality. They do not lock themselves into systems that resist correction. They accept that soil, climate, and economics change faster than doctrine. When indicators point to declining efficiency, they act early, while correction is still cheap. This mindset is what separates sustainable performance from ideological persistence. High-yield systems succeed not because they avoid disturbance, but because they manage it. In the next section, the focus shifts to the future. Not trends or slogans, but what scalable agriculture actually requires as pressure continues to increase. The future of high-yield agriculture will not be defined by methods, but by adaptability. As pressure increases from climate volatility, economic tightening, and biological limits, systems that cannot adjust will be abandoned, regardless of how well they once performed. No-till, as an absolute, struggles in this future. Absolute systems assume consistency. Adaptive systems assume disruption. High-yield agriculture now operates in the second category. Yield targets are high, margins are thin, tolerance for inefficiency is minimal. Under these conditions, the ability to intervene quickly becomes a competitive advantage. Adaptive systems treat soil management as dynamic. They accept periods of disturbance and periods of restraint. They measure outcomes continuously and recalibrate before losses accumulate. They do not confuse long-term vision with short-term rigidity. Technology accelerates this shift. High-resolution data exposes inefficiencies faster. Yield variability becomes visible earlier. Root and soil measurements improve. Systems that rely on surface indicators alone become obsolete. The farms that succeed will not defend practices. They will abandon them when necessary. Sustainability in this context is not about minimizing intervention. It is about minimizing waste. Wasted nutrients, wasted water, wasted potential. Any system that increases waste under pressure will be replaced. No-till will remain part of the toolkit, but it will no longer be treated as a foundation. It will be one option among many, deployed where it aligns with goals and removed where it does not. This is not regression, it is evolution. High-yield agriculture has always evolved by rejecting absolutes. The next phase will be no different. The final question is not whether no-till works. It is whether insisting on it makes sense when evidence says otherwise. No-till does not fail because it is inherently flawed. It fails when it is treated as untouchable. High-yield agriculture exposes this weakness because it operates without ideological safety margins. Every inefficiency is amplified. Every delay in correction becomes expensive. The central mistake is not adopting no-till. It is refusing to define its limits. High-yield systems demand functional depth, synchronized nutrient delivery, and structural resilience. When these requirements are met, no-till can contribute. When they are not, no-till becomes a constraint rather than a solution. What ultimately breaks high-yield no-till systems is not erosion, not biology, and not even compaction alone. It is rigidity, the inability to intervene when indicators point to declining efficiency. Agriculture is not a belief system. It is applied problem-solving under pressure. The farms that remain competitive will be those that treat soil management as engineering guided by biology, not biology constrained by ideology. They will disturb when necessary, protect when possible, and measure relentlessly. No tool will survive in these systems, but only as a tool, not as an identity. High yields do not reward purity. They reward performance. And performance always belongs to systems that can change.